All right, guys. Here I'm back with the last video we're going to do for Lewis structures. Real quick before we get into that, I want to talk to you a little bit about resonance structures, just to say that, okay, I know you see the slide, you're reading the text, you might see that. We're not worried about resonance structures a whole lot. All they're doing is saying that, hey, when you have a structure that can be drawn several different ways, so if we call this oxygen Billy, and we call this oxygen Bob, and we call this oxygen Mo, you know, Billy's got the double bond here, Bob's got the double bond here, Mo's got the double bond here. So since there's three different ways to draw it, technically we should draw all three of them and draw these little lines in between and say, hey, it's a resonance structure, there's multiple ways to draw it. We're not worried about all that, okay? You might come across one that you could draw as a resonance structure. I'm not asking you to do that, okay? Just wanted you to know what was going on with that, okay? So what we're going to do is we're going to get into that step 6 of the steps of drawing Lewis structures, the formal charge, the should minus has part that's been in there. You can do every example that we're doing. You don't really need formal charge. There's a couple problems that are exceptions that you're not going to be able to figure out without understanding formal charge. With the exception of that, you're going to be able to do all of them without formal charge. So don't get worried too much about formal charge. It's not that difficult. I think it helps us with a total understanding of everything with Lewis structures to go ahead and talk about it and do it. But don't get too caught up in it, okay? For the most part, and a lot of times formal charge isn't going to matter at all. You know, we've done all these problems so far. We haven't talked about any. There's some problems. Most problems it's not going to matter. Some problems it will cause us to adjust our answer and give a better answer than what we previously had. But let's not get too caught up in it for the most part. All right. So here's what I'll say to start off. Formal charge. What is formal charge? It's the actual charge of the individual atoms within the larger molecule or a polyatomic ion. The sum of the formal charges has to equal whatever the net charge. So if the net charge of the molecule if it's a neutral molecule, if the net charge is 0, then all the formal charges of the individual atoms in there has to add to 0. If it's a polyatomic ion like this guy, it's got a net charge of -1. So that means that the formal charge of each of these guys would have to add to -1. Okay? So the sum of the formal charges have to add up to whatever the whole net charge is. In most cases, that's going to be 0. All right? There's a complicated definition of what formal charge is. The should minus has is a much easier way to think about it. And I'll explain to you what that is in just a second. In general, here's the deal. We want structures to have as few formal charges as possible. Not only do we want the net formal charge to add, the net charge to add up to what all the formal charges add up to, or the formal charges add up to what all the net charge is, okay? But we want there to be as many zeros as possible. We want zeros across the board, okay? For each individual atom, we would like their formal charge to be 0, meaning they have no formal charge. Okay, so we want to have as few other things as possible, all right? Formal charge trumps the octet rule. There's times when you get to the 3rd period and below that where atoms can have overfilled shells. They can have, their octet rule can be broken by having more than 8 electrons, up to 12, okay? I'll show you an example of that. That's possible, but it's only possible when we're talking about stuff from the 3rd period down. So silicon, phosphorus, sulfur, those are popular atoms that do that. As far as above the 3rd period, you don't have to worry about breaking the formal charge with the exception of boron. Boron can break formal charge by having fewer than 8. A lot of times it'll just have 6. Okay? Formal charge would explain why. Formal charge always explains why the octet's being broken. And when the octet rule is being broken, it would always be broken by a central atom. It's never going to be broken by atoms around on the outside. It would always be broken by a central atom if the octet was to be broken. Okay? But a lot of times, formal charge isn't going to do anything. So let me show you this real quick here. I'm just gonna throw a problem on the board just to show you that nothing's really happening a lot of times. Well, my pen would work. There we go. So we got nitrogen trifluoride. Nitrogen's got 5, and then you have 3 of the fluorines. Each of the fluorine has 7, so that's giving you a total 21 plus 5, 26, right? So nitrogen is your central. You got your fluorines going all the way around, right? And then when you give everybody the 8 that they're supposed to have, just like that, you end up with your 26. 8, 8, 8, plus 2 more here, 26. Everybody's good here. All right, so when do you need to worry about formal charge? All right, when you look at a problem and all the atoms have the number of bonds that they want, then formal charge is not an issue. Don't even worry about it. Don't even think about it, okay? So when we look at this problem, fluorines, group 7, they have 7 valence electrons. That means they want 1 more. Remember, if you would take 8 and subtract the number of valence electrons, that'll tell you how many bonds they want. So if they have the number of bonds they want, this guy has 1, 1, 1. Fluorine wants 1 bond, so they're good. That means their formal charge will be 0. Nitrogen has 5 valence electrons. 8 minus 5 is 3, so nitrogen wants 3 bonds. How many bonds does nitrogen have? 3. So that means its formal charge is 0. So just like that, boom, 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 I just quickly said, hey, that one's good. Its formal charge is, there's all 0, so I don't even have to worry about it. You only need to think about formal charge if you come across the problem where you have an atom that doesn't have the formal charge of 0. In other words, they don't have the number of bonds that they want. So then you have to look and say, okay, can we do something to give it a formal charge of 0, to give it the number of bonds that it wants? Okay, so we look at this problem. I've already got it on the board to kind of save us some time here. This is a hydroxide. I've already got it built here. We're just going to say, okay, what is the formal charge of each of these atoms when you look at this? All right. So to start with, oxygen wants 2 bonds, right? Has 6 valence electrons, so that means it wants 2 more bonds. It only has 1 bond, so that means its formal charge is not going to be 0. Okay. So we can see that it does have 2, 4, 6, 8. Its octet's being filled. It's happy there. Hydrogen, it's good. It's got the 2 that it wants. In fact, hydrogen will always have a formal charge of 0. Don't worry about the hydrogens. You can completely ignore them. Okay? But for the other ones, what do you do to find formal charge? The should minus has is the easiest way to think about it. The should means how many valence electrons does the atom actually does that atom have, right? So oxygen, according to the periodic table, has 6 valence electrons, right? So that would be the should, 6 valence electrons. Now, the has means when you actually look at this problem, how many electrons does it have right around it? Okay? Now I know that there's 8 there. It's between its lone pairs and its sharing, there's 8. 2, 4, 6, 8. But that's not what we're talking about here when we're talking about formal charge. We're talking about just the electrons right around it. So if you would take and you would draw a circle around the atom, just like that, right? You count all the electrons in that circle. 2, 4, 6, and then this one, 7. That's how many it has. Okay? So, in other words, all of its unshared electrons, and then just half of the ones that it's sharing. So, you see how I drew the circle to cut the bond in half? You always draw the circle so it cuts the bond in half, and you just count the electron on the inside. You don't count the electron on the outside. Okay? So, 2, 4, 6, 7. That's how many it has. 6 minus 7 is -1. So, this oxygen has a formal charge of -1. We already said hydrogen is always going to be 0. So -1 plus 0 is indeed -1, right? And we said that it had to be equal to whatever the net charge is. The net charge is -1. So -1 plus 0, hey, that didn't change anything. It just told us that we were right, okay? Now, if we look at this problem, all right, we got this sodium or sulfur dioxide here. I've already built the problem like you would do if you were doing this problem this is where you would get, okay? You would end up with, as far as I got 2, 4, 6, 8, 10, 12, 14, 16, 18. I originally had 20, so then I had to add a double bond here to get us down to 18. Okay, I could have put the double bond on either side, but I put it on that side. Okay, so now we have 18. So according to the first 5 steps of the Lewis structures, we've done this right. But when we look at it, we're saying, okay, number of bonds that they want. Oxygen wants 2 bonds. It only has 1. So its formal charge is not going to be 0. So this is a problem that I would want to look at with formal charge to see if I could adjust it. All right. Now this guy, it does have a formal charge of 0. All right. Should have 6 because it's oxygen. Oxygen's 6 valence electrons. And you look, how many it actually has? 2, 4, and then these 2 right here would be 6. 6 minus 6 is 0. All right. But when you look at this guy, it's not going to be the same, right? Because there's only 1 bond there. So oxygen should have 6 valence electrons minus 2, 4, 6, and then that 1 makes 7. So once again, it's a negative 1. The sulfur, oops, I drew my circle too big. Let me make the bond longer. There we go. All right. My sulfur, once again, sulfur is in group 16 as well, so it should have 6 valence electrons. I'll put it up here. And how many does it actually have? It has these 2, and then 1, 2, 3. So 2, 3, 4, 5. Total of 5. 6 minus 5 is a positive 1. In terms of the net charge is 0, because it's a neutral atom, negative 1 plus 0 does indeed add to 0. So the net charge is right. But when we start talking about the whole structure having as few formal charges as possible, this being a negative 1 and this being a positive 1 is not the best case scenario, right? So formal charge is saying, hey, if we could adjust this so that these were both zeros, that would be better, all right? So that's what we're going to do. We're going to try to adjust it. And we're always going to go for the one that is a negative. You have 2 that is have a formal charge right next to each other, and they're opposite in sign. One of them is negative, one of them is positive. We're going to take 2 electrons off of the negative one, and we're going to move it into a bond with the positive one. When we do that, what it's going to do is it's going to make this formal charge go up. It's going to make that formal charge go down by 1. So watch. Since we did that, now when we look at this oxygen, start with, in terms of its octet, it still has its 2, 4, 6, 8 in terms of the octet, right? But in terms of formal charge, should have 6 valence electrons. That's what the periodic table tells me. And then I got 2, 4, and then I just count these 2. I don't count the other 2, right? So 2, 4, 5, 6. 6 minus 6 is 0. So we just improved that. And at the same time, we changed this one to be 6 minus, the first number's not going to change because that's what the periodic table tells me, right? 2, 3, 4, 5, 6. So 6 minus 6, this one right here is also 0. So do you see how we took 2 electrons and we put them in a bond? They were unshared. We put them in a bond, and that changed these formal charges, and now we've got more zeros. We have fewer formal charges, which is the goal here, okay? To have fewer formal charges. So this particular problem, formal charge did tell me to adjust it and to add 1 more bond. In the process of doing that, it caused me to break the octet rule here in the middle. So sulfur, we can see now in terms of total octet, it's got 2, 4, 6, 8, 10. But remember, sulfur is in the 3rd period. All right, so 3rd period and down, those nonmetals can break the octet and actually overfill, okay, because they have unused orbitals in the d orbital, okay? From the 3rd energy level on, there's a d orbital, right? So sulfur has a d orbital that's not being used at all, and in this particular case, it actually decides that it's lower energy to bond with both of these guys in this way, so that it's putting some of those electrons in that d orbital. Why? Because it's a lower energy and it makes it more stable. It can do it, it will do it, okay? So this guy has 10, it's broken its octet. Remember, only the central atom will break their octet. Only atoms that are third period and down will break their octet. But it did it, and it did it for the sake of formal charge. Formal charge explained to us why that was actually happening. Okay? So I will do one more problem with you super quick here, and we will be done with this. Once again, don't get too caught up in the formal charge. Try to use it anytime you see a problem where you have an atom that doesn't have the number of bonds that it wants. Look at it and see if that's just the way it has to be. Sometimes that's the case. Or if formal charge can adjust it to make it better. All right? So let's see. Let's pick one more problem here. We'll do this H2SO4. So 2 electrons from the hydrogen, 6 from the sulfur, and then 6 times 4 from the oxygen for a total of 32. Sulfur's got to go in the middle. We're going to go all the way around with oxygens. All right? And then we're going to put hydrogens on the end here. You see how this looks nice and symmetrical? Okay? Atoms naturally arrange themselves in a very symmetrical way, generally speaking. Okay? So you got oxygens going all the way around the sulfur, and then you got hydrogens attached on the end. Technically, the hydrogen could be up here, you could have them here and here, whatever, but you definitely have to have the oxygens around the sulfur and then the hydrogens on the end of the oxygens. Because hydrogens would be the end of the road. If you put a hydrogen up here, then you wouldn't be able to go past it. Remember, hydrogens are a dead end. All they can do is just have a single bond. Okay? So this is the most symmetrical way to do it. There's some problems that I'll give you where there'll actually be multiple carbons. All right? So what you do is you make all the carbons, think of all of them as being your central ones, and then you try to put the same thing on each of the carbons. You try to make it symmetrical. So you'll have a chain of carbons. You might have 2 or 3 carbons like this, and then you'll have hydrogens coming around them like this, or something like that. Okay? Not to say, it looks exactly like that, but it'll be something like that, so that it looks like nice and symmetrical most of the time. Okay? But don't think of, if you have more than one carbon, don't think of one of them as being central. Think of all the carbons as being central. All right, so sulfur's not central. I've got oxygens around it, hydrogens attached to the end. Let me give everybody 8 real quick. This guy needs 4 more. This guy needs 4 more. And then the top and bottom oxygen actually needs 6 more. Okay, like that. 8, 8, 8, 8. That gives me a total of 32. So in terms of step 1, step 2, step 3, step 4, and step 5, this is good, okay? But when I look at it, I'm saying, okay, maybe I should think about my formal charge here, because of course hydrogens are always good. This oxygen has 2 bonds, and this oxygen has 2 bonds, which is good. So that means their formal charge is going to be 0. They have the number of bonds they want. But these guys up here do not have the number of bonds they want. So anytime I have a problem where an atom doesn't have the number of bonds they want, then I'd say, okay, what about the formal charge? I do that step 6 in that case, okay? So when I look at this guy, oxygen, 6, should have 6 valence electrons. It has 2, 4, 6, and this one right here makes 7. So once again, it's a -1. This one down here is identical to it, so it's also 6 minus 7, which is -1. And then, I don't even know if you can see if I'm changing colors or not, but just in case. All right, when I look at sulfur, sulfur is also group 16, so it's 6, should have 6, and then how many it actually has is 1, 2, 3, 4, which gives me a +2. So right next to this positive formal charge, I have a negative formal charge. So naturally what these atoms do is they balance that out by shifting some electrons around in order to lower their formal charge, which lowers their energy and it makes it more stable. So once again, we move electrons from the negative one to bond with the positive one. So this is the negative formal charge. We're going to take those 2 electrons and we're going to move them into a bond. Okay? By doing so, it's going to change this number. It's going to make this formal charge go up by 1. So now I've got 2, 4, 5, 6. So now it's 6 minus 6, which is 0. Right? As far as the sulfur goes, the sulfur changed from having 4 to 1, 2, 3, 4, 5. So 6 minus 5 gives me a 1. Right? And then I can do the same thing on the bottom side here. Right? By taking a pair of these electrons and moving them into a bond, and that's going to change this negative because I took the electrons away from the negative and moved them into a bond. That's going to make that formal charge 0, 6 minus 6, and then that's now I have 6 minus 1, 2, 3, 4, 5, 6 here. So 6 minus 6 gives me a total of 0. So you see how formal charge told me that I needed to adjust. And now I have nothing but zeros across the board. 0, 0, 0, 0, 0, 0, 0. So it's completely zeroed out. It's got as few formal charges as possible. Now, did that cause me to break the octet rule? It did. When I look in the center here, sulfur has 2, 4, 6, 8, 10, 12 total electrons bonded to it or attached to it, right? But that's okay, because sulfur can break the octet rule. The reason it broke the octet rule is because of formal charge. Okay, for the sake of formal charge, it broke the octet rule. Formal charge trumps the octet rule. So this would be the correct answer to actually have it. If I clean it up real quick. Sulfur, double bonded with oxygen, double bonded with the other oxygen. Oxygen to hydrogen, oxygen to hydrogen, and cleaned up. That's actually the best answer, okay? But we couldn't get there without formal charge. Without formal charge, we would just have single bonds here, okay? So, hope that helps. Like I said, most of the problems you're going to do, that's not going to matter. Every now and then you're going to run across a problem where you're going to end up with an atom that doesn't have the correct number of bonds, the number of bonds that it wants, in which case then you will look at formal charge to see if it can be adjusted. If it can, you do. If formal charge, if it doesn't, if you can't do anything, sometimes you can't. Sometimes you might end up with a problem where you only have one formal charge, and that's just, it is what it is. It has to be that. Okay? So sometimes you can't always adjust and fix. But if you struggle with the formal charge, don't worry about it. You're fine doing everything before this video. If you can do the stuff that's in this video, then that's great. Okay? So, excellent. Let me know if you have any questions, and I'll get back with you.